I am ready to get into it.
Oh yeah, it's a classic. It's really at the heart of quantum mechanics, you know?
Yeah. And like, it seems so simple at first glance, right?
Sure.
Shine a light through two tiny slits,
Yeah,
and you think, okay, two bright spots on the other side.
exactly,
But then
yeah.
the universe is like, nah, I got something weirder in store for you.
It's like it's playing tricks on us,
Right.
but they're tricks that actually reveal a deeper truth, I think.
Okay, I like that. So help me out here. In the, like, normal physics world, the classical physics world, what were scientists expecting to see when they first did this experiment?
Well, in classical physics, you've got two basic types of things, right? You got particles,
Right, like little tiny tennis balls or something.
exactly, like little bullets and tennis balls. And then you've got waves.
Yeah, like on the ocean.
Yeah. So if light were just particles, you'd expect to see, like you said, two bright spots on the screen behind the slits, like they went straight through.
Right, like if I threw a bunch of tennis balls through two doorways, you'd have two piles on the other side.
Exactly. Yeah. But if light were a wave, you'd get an interference pattern. So think of like ripples spreading out in a pond, right?
Okay, yeah, I can picture that.
They kind of overlap and create these zones where the waves are bigger and zones where they cancel each other out.
Right, like those wavy lines.
Exactly, yeah. So going back to the double slit experiment, if light were a wave, we'd expect to see those wavy lines, those bands of light and dark on the screen.
Okay, so that's the classical picture. Particles are waves. Nice and neat. But that's not what happens in the double slit experiment, right?
Mhm.
That's where things get freaky.
Right. You hit the nail on the head.
So tell me, what did they actually see? Like, break it down for me. What was the mind-blowing result?
Well, the crazy thing is they saw the interference pattern. Even though they were shining light, which we know is made up of these little packets of energy called photons, right?
Yeah, photons, like little particles of light.
Yeah, exactly. So even though they were sending these photons one by one through the slits, they still got that wave-like interference pattern on the screen.
No way. So it's acting like a wave, even though it's made of particles.
Exactly. And that's one of the things that really blew people's minds back in the day. It's like, wait a minute, how can something be both a particle and a wave at the same time?
Yeah, that's where I get tripped up. Like, I thought we had figured out that light was made of particles.
And you're right, we did. But this experiment was like, hold on, there's more to the story. It's like light has this dual nature.
Okay, so it's not like it's switching back and forth like, now I'm a particle, now I'm a wave. It's like, it's both at the same time.
Yeah. That's the thing, it embodies both aspects simultaneously. We call this wave-particle duality, and it's one of the cornerstones of quantum mechanics.
And this doesn't just apply to light, right? I was reading that other particles, like electrons, do this too.
Absolutely. It's like the universe is playing by a different set of rules at the quantum level.
Okay, so this wave-particle duality is not just some quirky thing about light, it's a fundamental principle of how the universe works.
I think so. It's really mind-blowing when you stop and think about it.
And the thing is, it gets even weirder. The source I sent mentioned this idea of a probability wave. Like, what even is that?
Okay, so imagine this. We fire a single photon at the slits.
Okay, one tiny particle of light.
Right. Now you might think, well, it's got to go through one slit or the other. Right.
Right, like it can't go through both at the same time, can it?
And that's where it gets tricky, because we see the interference pattern building up, even when we send photons one by one.
Right, so it's not like they're all bumping into each other and creating the pattern.
Exactly. Each photon is somehow contributing to that wave-like effect on its own.
Whoa, okay, so how does that even work?
That's where this idea of the probability wave comes in. So the probability wave, it's not like a physical wave, like a water wave. Instead, it describes the probability of finding that photon at a particular point on the screen.
So the bright bands in the interference pattern mean there's a high probability of finding the photon there, and the dark bands mean it's less likely.
You got it. It's like the photon is exploring all possible paths through the slits simultaneously, and this probability wave is a way of describing this very strange behavior.
Okay, so it's not that the photon is a wave, it's more like the chances of finding it in a certain spot are what create that wave-like pattern. That's trippy.
It is, and it gets even weirder when we start talking about how this probability wave collapses.
Oh yeah, that was another thing in the source collapse of the wave function. I think I'm gonna need a little more explanation on that one.
So think of it this way. Before we measure where the photon lands, it's like it's in this fuzzy state of possibility, right?
Like it could be anywhere within that probability wave.
Exactly. But when we try to observe which slit it went through, when we try to measure its position, something really strange happens.
Okay, what happened?
The probability wave collapses. It goes from this spread out wave of possibilities to a single point. It's like the act of observing forces the photon to choose a specific path.
So just by looking, by trying to measure it, we're changing what's happening.
That's what it seems like. And this idea, the collapse of the wave function, it's one of the most mind-bending things about quantum mechanics. It suggests that our active observation is intimately connected to the reality we observe. It's not just a passive process of recording information, it's actively shaping the world around us.
Wow. Okay, I think I'm starting to get it,
Yeah.
but it definitely raises more questions than it answers.
That's the beauty of it, though. It makes you question everything you thought you knew about reality.
Yeah, no kidding. All right, so we've covered a lot of ground here. Wave-particle duality, probability waves, the collapse of the wave function. We're just scratching the surface, though, right?
Oh, yeah, we're just getting started. And trust me, it gets even weirder from here.
I can't wait. All right, so to recap, we're talking about light acting like both a wave and a particle, and this wild idea of a probability wave that describes where it might show up, and then the fact that just by looking, we might mess the whole thing up.
Yeah, that's a pretty good summary of what we've covered so far.
And you said this wave-particle duality, it's not just light, right? Like electrons do it too.
Yeah, electrons, protons, neutrons, all sorts of particles. They all exhibit this wave-particle duality.
So we're talking about the same electrons that are like, part of atoms.
The very same.
Yeah.
And this wave-like behavior of electrons, it has a huge impact on how atoms are structured, actually.
Oh, really? I hadn't thought about that.
Yeah, it's pretty mind-blowing. You see, if electrons were just particles, they would just spiral into the nucleus and the atom would collapse.
Wait, seriously. So the only reason atoms exist is because electrons are acting all wave-like.
Pretty much, yeah. It's because electrons act like waves that they can exist in these stable orbits around the nucleus.
I always picture those orbits like planets around the sun, like the little balls whizzing around.
Yeah, that's a common picture. But it's not really accurate. These electron orbits, they're more like blurry clouds of probability.
Okay, so it's not like the electron is physically a wave,
Mhm.
but the chances of finding it in a certain spot are what behave like a wave.
Exactly. And these probability clouds, they determine how atoms bond together to form molecules and basically how chemistry works.
So this wave-particle duality, it's not just theoretical, it's shaping the world around us.
That's exactly it. And it gets even deeper when we start talking about how this connects to the collapse of the wave functions.
Right, that was a big one.
Which, remember, is triggered by measurement.
So our act of looking at something, of measuring it, that actually affects its state.
Yeah, that's the crazy thing about quantum mechanics. It's like we're not just passive observers, we're actually part of the experiment in a way.
And this ties into that whole Heisenberg uncertainty principle thing, right?
Yeah, you got it. Heisenberg's uncertainty principle is all about how our active measurement inherently disturbs the system we're trying to observe.
Yeah, the name itself sounds kind of intimidating, I'll be honest.
It does have that ring to it, doesn't it? But it's basically saying that there's a fundamental limit to how precisely we can know certain pairs of properties of a particle at the same time.
Okay, so position and momentum.
Exactly. The more precisely we try to measure a particle's position, the less we can know about its momentum, and vice versa.
So it's like you can't have your cake and eat it, too, when it comes to knowing certain things about a particle.
That's a great way to put it. And the double-slit experiment, it beautifully illustrates this principle. Remember how measuring which slit the photon goes through destroys the interference pattern?
Yeah, it's like the act of measuring forces the photon to choose a path and stops it from acting like a wave.
Exactly. By pinpointing its position, we lose information about its momentum, which is directly related to its wave-like behavior.
So the act of measuring one thing, like position, messes up our ability to know the other thing. Momentum?
Precisely. It's like the universe is saying, you can only know so much. And this has really profound implications for how we understand the quantum world. It suggests that at a fundamental level, reality is inherently uncertain, and that our active observation is crucial in shaping that reality.
Okay, my mind is officially blown. Again.
That's a good sign. But here's the thing. There's still so much debate about what this all means. We've been talking about what's called the Copenhagen interpretation of quantum mechanics.
Right, I think that was mentioned in the source I sent.
It's the most widely accepted view, yeah. But there are other interpretations out there, too, like the many worlds interpretation, for example.
Oh, yeah. That one sounded pretty wild.
It definitely takes things in a different direction. In the many worlds interpretation, every time a measurement is made, every time that wave function collapses, the universe
Hold on,
splits.
splits? Like, what do you mean?
Right. It means that all possible outcomes of the measurement, they actually happen, but each in a separate universe.
So instead of the particle choosing one path, it's like all possible paths are happening simultaneously, but in different universes.
Exactly. So you've got this multiverse where every possibility is playing out.
Whoa, that's a lot to wrap my head around. So instead of one uncertain reality, there's like infinite realities where every possibility happens.
That's the basic idea. It gets rid of the problem of the wave function collapsing, but it also introduces the concept of all these parallel universes.
Yeah, it's kind of a trade-off, isn't it?
Right.
Okay, so we've got the Copenhagen interpretation where observation causes the collapse, and then many worlds where everything happens, but in different universes.
Right, and there are even more interpretations out there, like pilot wave theory.
Wow, so many ways to try to explain this quantum weirdness. It's amazing how one experiment, the double-slit experiment, can spark so much debate and inspire so many different ideas.
That's what I love about quantum mechanics. It's a field that's still evolving, still full of mysteries. And the double-slit experiment, it's really a gateway into those mysteries.
And you mentioned earlier that scientists are pushing the double-slit experiment even further these days. What are they up to?
Well, what if I told you they're now doing this experiment not just with photons or electrons, but with molecules?
Wait, molecules, like the things that make up stuff.
The very same. And not just small molecules either. They're doing it with big, complex molecules like buckyballs.
Buckyballs, those sound familiar. Like, aren't those soccer ball-shaped molecules?
Yeah. They're these amazing structures made of 60 carbon atoms.
And they're doing the double-slit experiment with those. So, like, a buckyball can go through both slits at the same time.
That's what the results seem to suggest. It's incredible to think that something so relatively large can exhibit quantum behavior.
So where does it end? Can you do this experiment with, like, a baseball? I'm still trying to wrap my head around that. Molecules behaving like waves. So where's the line? Can you, like, do this with a baseball? At what point does quantum stuff stop being so weird?
That's the million-dollar question, right? Like, where does the quantum world end and the normal world begin?
Right, because I don't see my coffee cup suddenly acting like it can be in two places at once.
Exactly. But as things get bigger, their interactions with the environment, like all the air molecules and stuff, they tend to disrupt those delicate quantum superpositions.
So it's like trying to balance something really delicate. Any little disturbance will knock it over.
Exactly. The bigger the object, the harder it is to isolate it from all those outside influences and see those quantum effects.
Okay, so it's not that quantum rules stop applying to big objects. It's just that it's harder to see those effects.
That's the thinking, yeah. But the fact that we see them even with molecules like buckyballs, it's really pushing the boundaries of what we thought was possible.
It's like the universe is saying, think you figured it all out. Nope, there's more.
Right. It's amazing, and it really forces us to rethink what we thought we knew about how reality works.
Definitely. And it's not just about, like, the particles themselves, right? We talked about how observation, the act of measuring, plays a role too. But the source I sent, it mentioned these delayed choice experiments. Those sounded pretty wild. Can you tell me a little more about them?
Okay, so imagine this. We've got the double slit set up, right?
Okay.
But we don't decide whether to measure which slit the particle goes through until after it's already passed through the slits.
So it's like we're giving the particle a head start
Yeah.
and then deciding whether to peak or not.
Exactly. It's almost like we're affecting something that's already happened. And the results suggest that our choice in the present can actually influence something that happened in the past.
Wait, hold up. Are you saying we can change the past? Like time travel stuff?
Not quite time travel, but it does mess with our ideas about cause and effect, right? It highlights how deeply interconnected observation and reality are in the quantum world.
So it's not just that we can't know everything with perfect certainty. It's that our choice to observe actually shapes what happens.
It's a wild idea, and it challenges us to really think about the role of the observer in the quantum world.
I'm starting to see why this double-slit experiment is such a big deal. It's not just about particles and waves. It's about the very nature of reality itself.
Exactly. And it's led to all sorts of mind-blowing ideas and interpretations. We talked about a few, like the Copenhagen interpretation and the many worlds interpretation.
Right, right. And those are just two of many, right?
Yeah.
There are lots of different ways to try to make sense of this.
Exactly. And one of the things I find most fascinating is that these interpretations, they're not just about explaining experiments, they're about grappling with deep philosophical questions about the nature of reality, observation, and the role of consciousness.
Okay, so we've got these incredible experimental results and then these mind-bending interpretations. Where do we go from here? I mean, what's the future of all this?
Well, scientists are constantly pushing the boundaries of this experiment. They're exploring new ways to control and manipulate these quantum effects. And this has the potential to revolutionize technologies like quantum computing and quantum cryptography.
I've heard about those things, but honestly, they sound like science fiction to me.
They do, don't they? But they're based on these same principles we've been talking about, the same weirdness of the quantum world. And who knows what other incredible technologies might emerge as we continue to probe these mysteries.
That's like the deeper we dive into this stuff, the more questions we uncover. But it's those questions that keep us exploring, right? It's the mystery that keeps us going.
I think so. That's what makes science so exciting. We're always on the edge of the unknown, always pushing the limits of our understanding. And the double-slit experiment, it's a constant reminder that the universe is full of surprises.
Well said. This whole deep dive has been an amazing journey. We started with light in two slits, and now we're talking about the very fabric of reality and the potential to revolutionize technology.
It's incredible, isn't it? And it all stems from this one simple experiment that continues to challenge and inspire us over a century after it was first performed.
Well, I want to thank you for joining me on this incredible journey through the double-slit experiment. It's been a real pleasure exploring these mind-blowing ideas with you.
The pleasure was all mine. And to our listener, keep questioning, keep exploring, and keep that sense of wonder alive. The quantum world is waiting to be discovered.
And who knows what incredible secrets it holds. Thanks for tuning in.